Welcome back to This Explainer. I was recently looking into the mechanics of adaptive navigation, and honestly, it poses such a fascinating thought experiment. I want you to imagine an artificial intelligence agent, something highly capable in a computer simulation, suddenly dropped into a completely unpredictable, messy physical environment. It has no pre-programmed space map. None. It has absolutely no idea what lies around the next corner, and the entire problem space is just obscured. So how does it figure out where it is, where it needs to go, and how to get there without causing catastrophic damage to itself? It's like navigating a maze in the pitch black. This is literally one of the most compelling challenges in modern artificial intelligence, and today we're going to explore exactly how these agents conquer the physical unknown.
So, how exactly do machines navigate without a map? Picture that agent dropped into a totally dark, unmapped warehouse. It can't just sit there and run a standard search algorithm to calculate a perfect path because it's missing a fundamental component, a transition model. It literally cannot compute what will happen if it moves 5 feet forward because it can't perceive what is 5 feet forward. Lacking this internal map, traditional offline planning leads to complete computational paralysis. The agent just freezes. It has to act in order to learn and simultaneously learn in order to act. It's a total paradox.
Okay, let's dive right into this. Here is our roadmap. 1. Navigating the unknown. 2. The competitive ratio scorecard. 3. The threat of dead ends. And 4. Learning real-time A*.
Section 1. Navigating the unknown.
To truly grasp the scale of this problem, we kind of have to frame our AI agent as a blind explorer facing this immense, unforgiving wilderness. And to do that, we need to understand the profound difference between offline and online search. Now, in traditional offline search, the agent knows the entire state space map and the transition model from the very beginning. Theoretically, it can sit in a dark room, compute a complete, mathematically perfect solution using its internal model, and then just execute that exact sequence of actions open loop. It's like a train running perfectly on a pre-laid track. But online search? That is a completely different beast. The online agent only knows its own valid actions and can only detect its current state via its sensors once it physically occupies that space. It can't predict the outcome of an action until it actually executes it. Therefore, the agent must constantly interleave computation with physical action. It has to process raw sensor data, take a tentative physical step, reevaluate its surroundings, and dynamically construct its state space map in real time. Suddenly, the latency and computational cost of perception become a massive factor.
Because this online agent is building its understanding step by step, it faces a continuous, really high-stakes dilemma, the trade-off between exploitation and exploration. If you're familiar with probability theory, this is conceptually very similar to the classic multi-armed bandit problem. Exploitation means the agent leverages the paths and the structural information it has already uncovered to guarantee it makes incremental progress toward the goal. It takes the safe, known route. But if the agent solely exploits its limited knowledge, it might lock itself into a terribly inefficient, winding path. Exploration, on the flip side, means the agent actively chooses to visit completely unfamiliar states, hoping to discover hidden shortcuts or vastly superior routes. An advanced online agent has to constantly juggle these two behaviors. It's essentially calculating the expected utility of the path it already knows against the mathematical probability of finding a better path in the great unknown.
Section 2. The competitive ratio scorecard.
Now, you might be wondering, if our active agent is essentially flying blind, how do computer scientists actually measure its success? The answer lies in a mathematically elegant metric known as the competitive ratio. This is a form of worst-case analysis used specifically for online algorithms. See, because an online agent literally cannot calculate an optimal global path in advance, we evaluate its performance by comparing it to an algorithmic upper bound, an agent that actually can. We calculate the competitive ratio by taking the total actual path cost that our active online explorer incurs, and we divide it by the path cost that an omniscient offline agent would incur to solve the exact same problem. This omniscient agent acts as a perfectly informed planner that knew the entire map and all the obstacles beforehand. So what we are fundamentally measuring here is the penalty the agent pays for its initial ignorance.
The absolute holy grail of online search algorithms is to drive that competitive ratio down to exactly 1. If an algorithm achieves a competitive ratio of 1, it means the actual physical cost incurred by the initially blind online agent is perfectly equal to the optimal cost achieved by the omniscient agent. Basically, the agent navigated perfectly on the fly as if it had a map all along. But it's absolutely crucial to realize that in highly complex or adversarial physical environments, achieving a competitive ratio of 1 is virtually impossible. I mean, every exploratory detour incurs a real physical cost. So in reality, 1 acts as a theoretical ceiling, a mathematical limit that engineers are constantly trying to push their algorithms toward by heavily refining their heuristic functions.
Section 3. The threat of dead ends.
This brings us to the ultimate tension of online navigation. In the unknown, a single exploratory mistake can be fatal. The absolute greatest hazard in any online search is an irreversible state, widely known as a dead end. In graph theory terms, a dead end occurs when an agent traverses into a node that lacks any outward edges, returning to the strongly connected component of the graph, and it lacks any path to the goal node. The agent is utterly and permanently trapped. Now, think back to that competitive ratio metric we just talked about. If an agent falls into a structural trap like this, the competitive ratio suddenly spikes to infinity. The total path cost becomes incalculable because the agent can never actually complete its task. The algorithm just fundamentally fails.
Let's ground this graph theory in some vivid physical reality for a second to really understand the stakes here. Imagine an autonomous robotic rover exploring a collapsed building. If that rover calculates a path that involves driving down a steep, rubble-filled flight of stairs, it almost certainly lacks the mechanical traction to drive back up. That is a physical dead end. Or picture an autonomous drone navigating a dense subterranean cave network. It flies into a narrow, highly structured crevice to explore a potential shortcut. Suddenly, its spatial sensors detect proximity alerts from all 360 degrees. The space is way too tight for its propellers to alter pitch and reverse out. It is physically wedged into the rock. The computational panic of that moment is very real. It's an irreversible failure where millions of dollars of hardware are just lost due to a single bad heuristic estimate.
Because dead ends entirely break online algorithms, researchers often have to create a sort of theoretical safety net before deployment. To guarantee an online search algorithm will eventually succeed, engineers typically pre-process the state space if possible, or they operate under the strict assumption that the environment is safely explorable. In mathematical terms, this assumes the state space graph is strongly connected. It essentially guarantees that no matter what obscure state the agent wanders into, there is always at least one valid sequence of physical actions that can safely route the agent back to its starting position or onward to its goal. By assuming strongly connected components, researchers mathematically eliminate inescapable traps, which allows the algorithm to focus purely on path optimization rather than basic survival.
Section 4. Learning Real-Time A*. So, assuming we are actually working within a safely explorable space, how does an agent actually navigate it efficiently? Well, this introduces the algorithmic hero of our analysis, learning real-time A*, or LRTA*. Now, most people familiar with computer science know the standard A* algorithm, right? It's a foundational pathfinding tool. But standard A* completely fails in an online setting due to what we can call the teleportation problem. See, standard A* maintains a priority queue of frontier nodes. It might expand a node on the east side of a map and then seamlessly jump to expand a node 10 miles away on the west side of the map just because it happens to have a lower estimated cost. But an online agent cannot magically teleport across the map. Moving its computational focus requires actual, physical traversal, which incurs massive path costs. LRTA* was engineered specifically to solve this exact issue. Instead of maintaining a global, teleporting frontier, it behaves like a local hill climber, only evaluating the immediate neighboring nodes it can physically step into. But it overcomes the classic pitfalls of simple hill climbing by dynamically updating its memory as it moves.
The mechanics of LRTA* operating in the wild follow a truly beautiful four-step sequence. Step 1 is look ahead. From its current physical state, the agent uses its immediate sensors to detect all locally available next states. Step 2 is evaluation. For each of these immediate neighbors, the agent calculates a localized total cost estimate. It adds the physical step cost required to get to that neighbor, plus its current heuristic memory of how far that neighbor is from the ultimate goal. Step 3 is action. The agent physically executes a move to the neighbor presenting the lowest estimated total cost. And step 4, which is absolutely the secret sauce of this whole algorithm, is learning. Just before the agent leaves its old state, it updates its internal memory. It overwrites the estimated cost of the spot it is currently standing on with the new, mathematically exact value it just calculated from exploring the neighborhood. The source material points out something utterly fascinating about this specific learning step. By updating its memory to a higher, more accurate value, LRTA* effectively prevents itself from getting stuck in infinite loops.
Think about it. If an agent wanders down a massive detour or hits a localized dead end that forces it to backtrack, that Step 4 learning mechanism forces the agent to raise the cost estimate for that bad state in its memory. It is essentially creating an artificial slope, or a mathematical gradient, that heavily penalizes the path it just took. So, on future passes through that exact same sector, the agent will naturally slide away from that state because its recorded cost is now artificially high. Over multiple runs through the exact same environment, simply by raising the cost of its past mistakes, LRTA star smoothly and inevitably converges on the true optimal path. It's brilliant.
This leaves us with a really profound realization. If machines can learn to flawlessly navigate the physical unknown simply by acting, evaluating, and heavily penalizing the exact cost of their detours, the implications are just staggering. We are talking about Mars rovers autonomously navigating unmapped craters without having to wait for a 20-minute signal delay from Earth. We're talking about autonomous submersibles mapping the deep ocean trenches in real time, or even surgical nanobots actively navigating the highly complex, dynamic environment of human tissue to deliver targeted medicine. Active online learning isn't just about finding a path through a dark room. It is fundamentally about giving machines the autonomy to safely discover the world for themselves. Thank you so much for joining me for this explainer. Keep questioning and keep exploring.